So hello, welcome to another day of physical science. Today I am going to finish electricity and magnetism, finish chapter 8, which once again is the last chapter on your second exam. So yeah, we're going to jump right in. We had just gone over Ohm's law quite a bit and talking about resistors, and we're going to spend most of today really talking more about Ohm's law and resistors, but a little bit of magnets afterwards. About half magnets, half Ohm's law. So the first thing I want to talk about is so far we've been just talking about current, and we just said current, its symbol is I, it's in amps, and we haven't gotten into any detail on it. Really, current is a little more complicated than I've been glossing over. You see, when people first had the idea of current electricity, they did what is called direct current, or DC. When I say current, I normally mean DC. What that is a constant stream of electrons moving in one direction. And that's how we described with what current was, the charge over time or thing. It's just a flow of electrons. The thing is, this does not work well over long distances. In fact, DC can't travel. Yeah, it can't travel very far. A battery will always give DC current. And when I talk about current, you can normally assume I mean DC. Um, AC current stands for alternating current. That is actually what's in our walls. That's what comes out of an outlet. Where instead of the electrons going vroom, down a wire, they just do and bounce back and forth within the wire. And what happens is you have a current of the electrons going one way, and then a current of the electrons going the other way. And they're going one way, then going the other way. The thing is the electrons don't need to travel. With DC, the electron's going to go from one end of the wire all the way down to the other. In AC, they don't need to go anywhere. They just back and vibrate a little bit. And so AC works real well over long distances. And it's actually easier to make AC current than DC current. That gets into a very complicated reason why. But is what you normally have to deal with when doing electricity coming from, the wall as opposed to a battery. Thing is, it is so much more complicated mathematically when you get into things like impedance. The history between these two is so kind of crazy, though. DC current was mostly worked out by a man named Thomas Edison. You've probably heard of him before. AC current was worked mostly by Nikola Tesla, who died penniless, alone, and poor because Thomas Edison made his life goal to discredit Tesla and make sure that happened. Nikola Tesla is probably the closest thing we've had to a real life mad scientist. He's the first person to work out radio waves. He invented radar. He invented the first electric motor. He worked out how to make neon lights. He had a way to do wireless communications. Um, but basically, Tesla and Edison started a feud. Edison had a lot of money and made it, it made his life goal to make basically discredit Tesla. Um, Side note: the car Tesla is named after him because they use his engine. Like the engine in a Tesla is the one Tesla created back then. Um, it's kind of crazy all the stuff with him. Like in the feud, Edison was he was paying street urchins to pull animals off the street for him to electrocute them in front of people to prove how dangerous AC power was and why we should use DC. If Edison had won the electricity wars, if we did have DC power in our walls, you would need a power plant on every block of a city. In an area like this, you probably wouldn't have power unless you had your small little power plant. That's why we use AC. It's why Tesla won this. Even though, as I said, um, things didn't necessarily go great for him. I do recommend these two links. One is a drunk history of the feud between them. It's hilarious. The other one is from the Oatmeal. It's just a thing about how fucking crazy Tesla was. I recommend it. It's pretty nuts. Um, but yeah. Now, when we're talking about AC, most people say AC current or talk about DC, they say DC current. This is kind of a dumb sentence because AC stands for alternating current. So if you say AC current, you're saying alternating current to current. And if you say AC voltage, you're saying alternating current voltage, which makes no sense. It is word-wise dumb, but it just is what the word is. And as I keep saying, AC current works real well over long distances because you don't need to worry about electrons moving far. Now, in a wall outlet in America, we work with a 60 hertz frequency for AC current. What that means is the electrons go one way and then back. They do that 60 times in a second. That is the frequency, just like we talked about 2 chapters ago. We normally work with a 120 volt, 60 hertz frequency. That's just saying what the size of the voltage is and how quick they jump. The nice thing is Ohm's law does work with both AC and DC. As I said, I'm going to assume we're using DC as we move forward for ease. But if you have anything else like capacitors or inductors, which we're not going to get into detail in this class, it gets complicated. Very, very complicated. Any questions though? Okay. Often in a circuit, you will have more than one resistor. And if you have multiple resistors, you can hook them up 2 different ways, what is called series or parallel. In series, what it is all of your resistors are hooked up in a line. Like, once again, old school light bulbs are just resistors. And so a series circuit would just be one light bulb hooks up to the second light bulb, which hooks up to the third light bulb. You line them all up. Parallel is when all of the resistors are all hooked to the same points. That instead of putting them in a line, so the left of this guy goes to the right of the next one, and the left of that one goes to the right of the next one, and so on. In parallel, what you do is you put all the resistors and hook them all up to one spot, and hook that spot up to the battery. That the positive and negative terminal of the resistor, all of those are hooked together. Now, there's some kind of interesting effects of series and parallel. And it actually will affect how the voltage and the current will exist in the circuit. When you are in series, and I'm going to just start with 2 resistors in series. I'm going to simplify it, but this will work for more. If you have 2 resistors in series hooked up to a battery, what you'll have is a current will flow through the first resistor, then flow through the second resistor. Anytime you're in series, because they're connected directly together, the current will be the same within each resistor. That the current on resistor 1 will equal the current through resistor 2, which will equal the equivalent current that goes through the battery. The reason for these all being the same is because it's just electrons are just flowing through in one out the other. And what I can say is I can say if I have 2 resistors in series, I can talk about what we call the equivalent resistance, or REQ, where the equivalent resistance would be what would happen if we just had one resistor. See, I can say the voltage drop on resistor 1 will be the current through the resistor times the resistance of resistor 1. And the voltage drop on resistor 2 will be the current through the resistors times the resistance of resistor 2. And both of these have the same current. But the total voltage drop over the resistors must equal the voltage put out by the battery. And so the voltage of resistor 1 must equal the voltage on the voltage from the battery must equal the voltage on 1 plus the voltage on 2. But the voltage on 1 plus the voltage on 2, that would just be I1 R1 plus I2 R2, or IR1 plus IR2. I can kind of do some interesting thing here and pull this out separately. And what I get is that anytime you have resistors in series, it will be the same as if you just had one resistor. One resistor with an equivalent resistance that is the sum of the resistors. And so if I hook a bunch of resistors up in series, this is a bunch of resistors in series. What's going to happen is they'll glow. They'll all glow the same brightness. They're all going to get some current. And the current through light bulb 1, 2, 3, 4, and 5 will all be the exact same current. However, the voltage between them will not be the exact same. And I can say that these 5 light bulbs are the same as I had 1 light bulb that resistance equals the sum of the resistance values. Now, of note, in series, I don't remember if I did this in the video. We're going to see if I did it or not. Nope, I did not. If I removed 1 light bulb, the whole circuit would go. That if 1 light bulb blows, the whole thing's dead. That's because it's just in a nice line. Also, they're kind of dim. They're kind of dim because they get a fraction of the voltage. These each have the same value for resistance, so they each get a fifth of the voltage. It won't always be like that if the numbers are different. But the voltage will be spread out among them. And since voltage is kind of going to affect how bright the light bulb gets, it gets spread out. Very few, seldom do you really want to line things up in series. Once again, the whole if one blows, the whole thing blows. Christmas lights are usually put in series, or at least older Christmas lights, because it was easier to do. And that's why when one light bulb goes, the whole thing goes. That's the logic why. However, if you put things in parallel, if you make it so that both sides of, you make it so each side of the resistor goes to each side of the other resistor, goes to each side of the battery, what you'll get in parallel is that each resistor in parallel will get the same voltage. That the voltage on resistor 1 equals the voltage on resistor 2 equals the voltage of the battery. However, they will not each get the same current. See, with V equals IO, I can rearrange and say I equals V over O. And the voltage on, the current on resistor 1 will be the voltage over resistor 1. The current on resistor 2 will equal the voltage over resistor 2. And the current that actually goes through the battery will just be the sum of those, being V over R1 plus V over R2. I can kind of factor out the V and get this equation. And this gives you what happens when you have multiple resistors in parallel. If you have multiple resistors in parallel, it would be the same as one equivalent resistor, where 1 over the resistance of the equivalent resistor equals 1 over R1 plus 1 over R2. And if you have more resistors, it's just the sum of each one. Now note, 1 over R1 plus 1 over R2 plus 1 over R whatever is not the equivalent resistance. That is the inverse of the equivalent resistance. You need to do 1 divided by that number to get the equivalent resistance. However, when you put multiple resistors in parallel, the more resistors you add, the lower the resistance gets, which is kind of weird. And you have less current to go around. But the thing is if you remove one object, it all keeps going. If I turn off this light, my computer doesn't turn off. That's because they're in parallel. And also, everyone gets the same voltage. If I take my light bulbs and I go and put them in parallel instead, which I can put them in parallel by flipping all these switch and turn it back on, they're all much, much brighter than they were in series. They're all much, much brighter because they're all getting the same voltage. Where here, they got very little voltage. The 120 volts of the wall got split between them. But here, they're each getting the 120 volts of the wall. Any questions, though? Now, it is of note if you have only 2 resistors in parallel and this only works in 2, you can mathematically get a simpler equation. What it is I can find a common denominator, multiply the first one by R2 over R2, and multiply the second one by R1 over R1. Add up with the common denominator, that inverse. This equation right here will work for the equivalent resistance in parallel when you have only 2 resistors. But in general, in series, all the resistors have the same current, and the total voltage over all the resistors will be that of the battery. And the equivalent resistance is just add them up. In parallel, all the resistors have the same voltage, and the total current is the sum of the currents. And this equation gives the sum of the resistances. Questions? Okay, on the homework and the lab and the exam, I'm going to deal with resistors in parallel and series. So I'm going to do 2 example problems, one for resistors in parallel, one for resistors in series. And what it is I often ask for the current and voltage on each resistor. So let's start with a parallel. And let's say I have 3 resistors in parallel, a 6 ohm, another 6 ohm, and a 3 ohm. What is the total resistance when connected in parallel? And what is the current and voltage on each resistor when hooked up to a 12-volt battery? If I want to first find what is the total resistance in parallel, what I can say is in parallel, 1 over the equivalent resistance is 1 over R1 plus 1 over R2 plus 1 over R3. And so I'll just say 1 over 6 plus 1 over 6 plus 1 over 3. Well, for the record, 1 over 3, that's the same as 2 over 6. I'm just finding a common denominator. And so 1 over 6 plus 1 over 6 plus 2 over 6, that's 4 over 6. That is not the equivalent resistance, though. That's 1 divided by the equivalent resistance. 1 divided by RP is 4 over 6. If I invert both sides, I'll just flip it. That means RP is 6 over 4, which is equal to 1.5 ohms. And so when you hook up these resistors, the 6 ohm, the 6 ohm, and the 3 ohm, this is as if I had just one resistor with a resistance of value of 1.5 ohms. Any questions though? Now I also ask, what is the current and voltage of each resistor? In parallel, voltage is easy. In parallel, the voltage of each resistor is 12 volts. If they are in parallel, they will all have the same voltage as the battery. And the battery is 12 volts, so they all have 12 volts. If I want the current on each one, for current, I'm going to go to my circle and say to solve current, current is voltage over resistance. And I'll say this is how I get the current, and I'll do it for each one. The current on the first one is the total voltage over the resistance of the first one. The current on the second one is the voltage over the current of the second, or the resistance of the second one. And the current of the third one is the voltage over the resistance of the third one. Just for the record, if I add that up, 4 plus 2 plus 2, that's 8. 8 would be the current through the battery. Any questions though? Okay, let's take the exact same resistors and put them in series. And if they're in series, what's the total resistance of the circuit? And what is the current and voltage of each resistor? If they are in series, if you want the total resistance, you just add them up. The total resistance is just R1 plus R2 plus R3, which in this case is 6 plus 6 plus 3, where 6 plus 6 plus 3 is 15. That's the equivalent resistance. Now, if they are in series, that means they each have the same current, where the current through them is equal to the current through the battery. The parallel is easy. I just say parallel. It's just whatever the battery is. To get the equivalent current, though, you need to put some thought into this. What it is I will use my R equivalent to find I. I'll say the current through the battery is the voltage through the battery over the resistance of the equivalent circuit. I'll just say the current through the battery is V over the value I just found. Is the 12-volt battery divided by the 15 ohms from adding them together. This tells me that the current through the battery is 0.8 amps. That means the current through resistor 1 is 0.8 amps. The current through resistor 2 is 0.8 amps. The current through resistor 3 is 0.8 amps. And that's how you get the current through each battery. Once again, in series, you have to find the equivalent resistance and use the equivalent resistance with the voltage of the battery to get the current through each one. Questions though? To get the voltage through each one, I'll just say V equals IL. And V1 will be IL1. V2 will be IL2. And V3 will be IL3. Now note, I get 4.8, 4.8, 2.4. If I do that math, 4.8 plus 4.8 plus 2.4, I get 12. That's good. The sum of those must be the voltage of the battery. If they're not the voltage of the battery, something went wrong somewhere. This will show up on the exam, and it will show up on your next homework. I highly recommend you do the homework before the exam for practice. Let me know if you need a hand, and I will give it. It's probably the most complicated part of this chapter. So please, is anyone stuck before I continue? Okay. Let's talk about something else. I'm going to actually leave electricity at this point entirely. And I'm going to talk about magnets. Magnets are actually very related to electricity. Most of the relationships, though, we're not going to get into at this level. You really need calculus to get into how they're related. Natural magnets, which were called lodestones, were first found 6th century BCE in Greece. It was found in a place called Magnesia, hence the name. And the logic was people said, if I put this guy next to this guy, they pull together. The reason why is because the gods will it so, and they want to be near each other, and we're separating spirits otherwise. It was all supernatural logic. Around the 1st century BCE, so good 500 years later, people in China learned how to create magnets. And they realized that if they took a natural magnet and held it up against a piece of metal long enough, they could make their own magnets. And they used this and developed the first compass. But it was kind of like, cool, these things go do this. I put this magnet and it points north. That was understood. I put this guy near that guy. It pulls it up towards it. Cool. But people didn't necessarily understand how they worked. They knew they worked. They knew what they did, but not why. Well, here's the logic. Magnets have what is called a north pole and a south pole. They're commonly called dipoles because they have 2 poles. Di means 2. The naming convention is because if you have a ball magnet and you just let it be, the north pole will point to the north pole of the planet, and the south pole will point to the south pole of the planet. This actually is a very bad idea. Once again, naming convention before people understood, because magnets follow the same rule of attraction and repulsion as charged particles. You see, if I take these 2 magnets, if I try to put the 2 similar poles facing each other, they are going to repel. And in fact, if I try to hold them together and let go, that's going to shoot. Oop, I should make sure that's on the screen. It's going to shoot right out from the one into my other hand. That's because I'm either putting the north up against the north or the south up against the south. I don't know which. But if you take the north pole of a magnet and bring it close to the south pole of a magnet, they'll attract into each other. And it's the same idea. North attracts north. Oh, sorry. North and south attract each other. Opposite poles attract. But you have the same pole, either north with north, or if I flip both of these, oh no, flip this one, or south with south. Yeah, let's grab another one. You're gonna have repulsion. That's just if it's north with north or south with south. Okay? This is kind of annoying because it means the north pole of a magnet points to the north pole of the world, but north attracts the south. So really, it means everything's backwards and weird, but we're going to ignore that for a moment. Now, part of the reason we call magnets dipoles is that they do repel or attract by a distance of r squared, just like Coulomb's law for charged particles. But a magnet always has a north and south pole. You can never have a magnet with only a north pole or a magnet with only a south pole. So I want to check. Okay. If you ever try to take a magnet and cut it in half, you end up with creating a new north pole and a new south pole. And if you cut that in half, you end up with a new north pole and a new south pole. That you can never have a magnet with only a north pole or only a south pole. All magnets will always have a north and a south. And so, yeah, if I somehow split these magnets in half, which wouldn't be necessarily easy with the tools I have, let me do this so I don't have to lean so far. If I somehow split these magnets in half, they would each have a north pole and a south pole, each half. I cannot have one without the other. Okay. Now, when we had charged particles last chapter, we talked about electric fields. Just like electric fields, we can have magnetic fields. Magnetic fields are represented with the symbol B and are measured in the unit of Tesla. Tesla as in Nikola Tesla, who we just talked about. B fields are very easy to visualize. One of the easiest ways is you move a compass around a magnet, it'll be which way the compass points in each direction. Another object is just take ion fillings and put ion fillings around a magnet. This video I'm about to play is a bunch of ion fillings suspended in like some gel. And the white thing in my hand is a magnet. When I slide this magnet in, you can see all the ion filings start to move. And they eventually make this pattern that kind of matches the figure in the lower left. That is the direction of the magnetic field. That's just saying where a magnet will point and how it goes, with one side being the north side, one side being the south side. Okay? Questions? Now, when we talked about light a little bit ago, I said that light is an electromagnetic wave. It is a what a light is a E field and a B field oscillating. That is the electric field and magnetic field just doing this. This is because a change. Okay, this gets complicated, but they directly affect each other. That when you start having an electric fields can cause magnetic fields. And when you have magnetic fields can cause electric fields. It's actually more based off a change in electric field can cause a magnetic field, or a change in magnetic field can cause an electric field. And this actually causes a whole series of links. This is because what magnetism is the spin of electrons. More on that in a second. But anytime you have a current carrying wire, you create a magnet where the strength and field would be proportional to the current in the wire. Also, wires are attracted to magnetic fields. That if you have a magnetic field and you put a wire near it, it'll get pulled in. This is why people sometimes talk in very precise electronics as with magnetic shielding. Is because if you have a current, it creates a magnetic field. If you have a magnetic field, that can affect a current. This can cause a pretty crazy downhill loop, or sometimes a useful one. A GFI outlet uses this fact to create a safer outlet. So the question is, though, how the hell does this work? And the general idea is in a permanent magnet, spelled wrong there, but I'll come back to that. Well, no, it's spelled that way on purpose. It looks like it's spelled wrong because you're thinking the word permanent, but a permanent spelled like that is a way to talk about a permanent magnet. I don't know why permanent magnet uses the word permanent spelled differently. It does. I'm sorry. But in a permanent magnet, we talk about the electron spins. And what we say is an electron is like a ball, and it can spin. It can spin one way, or it can spin the other way. And if something spins, if you curl your right hand in the direction it's spinning, your thumb is the direction of the electron spin. Fun fact, this is not what's actually happening. Electrons cannot be viewed as solid balls. They're wave particles. It's much more complicated. This gets stupidly complicated, but here's the thing. If you pretend they're balls and spinning, all of the math works. And so for the longest time, physicists have just said, you know what? Let's just pretend this anyways. We acknowledge this is not what's happening, but if we claim this is what's happening, our math works. So this is happening, really, even though we fully know it's not what happens. Yeah, physics is weird. What happens is when an electron spins, it'll cause a small magnetic field. And in a random hunk of metal, like this piece of my pen right here, is not magnetic, doesn't attract anything else. But, okay, it is not going to attract that. Let me find something magnetic. There we go. This tape measure is right now not magnetic. It's not going to attract anything else metal. That if I bring it towards metal things, nothing's going to happen. What's happened is all the electrons in this tape measure are just pointing every which way. They're just each going. And each of these little electrons will act like a little ball magnet. And each ball magnet pointing in a random direction. But since they're pointing in random directions, they'll all cancel each other out. The thing is, if I bring a magnet close, didn't like that size much. If I bring a magnet close, what's going to happen is process of bringing a magnet close is going to cause the magnets, the electron, it's going to cause the electron spins to shift within the metal. This is a lot like the charge bipolarization we talked about with charge. And when I bring another magnet close, it will align all of the the magnetic dipoles. When all the magnetic dipoles or all the spins line up, they'll all point in the same direction. And if they all point in the same direction, instead of canceling each other out, they'll line up. And they'll say, hey, we're all going this way. And they'll act like a magnet. And so this isn't a magnet. It doesn't act like a magnet. But in the presence of a magnetic field, it acts like a magnet. Because when I put this guy here, it makes everyone else line up and act like a magnet. It's a magnet now. Once I take this away, not a magnet anymore. Now, anything that's highly magnetic is usually called ferromagnetic. This is things like iron, nickel, cobalt, and some others. And what happens is in a ferromagnet material, the magnetic fields of many electrons will form this magnetic domain that everyone lines up. And so, yeah, it won't be a magnet initially, but if you put it in a magnetic field, it can turn it into a magnet. Now, some materials can change their dipole easily. This tape measure is not magnetic. I put this here, it becomes magnetic. I take it away, it stops being magnetic. That's because the dipoles can move easily. That they'll go from being magnetic to just freely doing whatever the hell they want at will whenever they want. Things that make up permanent magnets, like the ones that I've been playing with this entire time, what they are is they cannot freely change. That the electric dipoles just stay where they are. And so if you manage to line them all up, they'll stay lined up. And it can always be magnetized. Versus this guy that they're just constantly moving. They don't care. So if you force them to line up, they'll line up. But the second you turn your back, they'll back to all over the place. Any questions though? Another way to make a magnet is the electromagnet. If you put a coil of wire around a piece of iron, if you put electricity through it, you'll have a magnet. Here we go. Right here is I have my coil of wire. And as I move it around, it's not doing anything to these paper clips. I turn it on, it attracts the paper clips. I turn it off, it doesn't attract the paper clips. Turn it back on, it attracts the paper clips again. This is an electromagnet. The general idea is that a current carrying wire creates a magnetic field. And so if you have a current carrying wire, you can make all the domains line up in the metal it's surrounding. You turn the magnet off, they'll go back to doing whatever the hell they want. And it's a good way to make a controllable magnet, just because a current carrying wire creates a magnetic field. Okay. Now, I've already kind of said this for non-electromagnets. There's two types, hard and soft. So hard magnets are like these permanent magnets. They're hard to make a magnet magnetized. But once they are magnetized, they'll stay magnetized. These guys are not going to stop being magnets anytime soon. Because we can the spins will stay wherever you put them. Soft magnets, really easy to magnetize, but they don't stay magnetized. This was a soft magnet. That when I put it here, it's a magnet. When I take it away, it's not a magnet anymore. Here, let's move that closer. Boop, magnet, boop, not magnet. Your front of a fridge is a soft magnet. What you use in electromagnets, that's normally a soft magnet. It doesn't mean it's soft. This guy is pretty hard. I wouldn't call it soft by any stretch, but that's why. A lot of you who do more electrical or do more work often try to magnetize screwdrivers. If you magnetize a screwdriver, you get the screw to stick to the end. Screwdrivers are normally made of metals that are kind of soft, kind of hard. They can keep a magnetic field, but it dies with time. And what it is how to make a magnet is you just put it up against another magnet. And if you put a magnet up against a magnet, it becomes a magnet itself. Something like a screwdriver, you keep it in a magnetic field long enough, will become magnetic. And you'll know if you have a screwdriver you magnetize that over time it becomes weaker. That's because slowly the spins stop lining up and go back to random. But if your screwdriver is no longer magnetic, just put it in a magnetic field for a while again. They actually make things to magnetize screwdrivers if an old one is losing the field. Questions there? Now, the biggest magnet of them all is the Earth. Well, it's not the biggest, because there's other planets that are bigger. But the biggest one we deal with is the Earth. Earth is a huge magnet with a magnetic field. It's why compasses work. It's why we have the Aurora Borealis and Aurora Australis. It's how birds navigate. It causes all sorts of stuff. The general thought is that it's due to Earth's rotation and the metal that makes up the core. Although I just saw a thing in the news like 2 weeks ago that we might have greatly misunderstood how the core of the planet is. And that's fun. But the Earth in general does act like a magnet. And the magnetic field of the Earth looks the same as a ball magnet. But here's the thing. We defined north as the direction the north point of a magnet points. But the north point of a magnet will point to south. North repel, right? North repels north. North attracts south. Well, north is the one with these little pieces of clay hooked up. And so if I have, oops. Oh no, I guess one's north, one's south. I take that back. I thought they were both north, but this was used for something I made and then broke just for this demo. But yeah, the north pole of a magnet attracts the south pole of a magnet. The north point of a magnet repels the north point of a magnet. Bounced off my hand and came right back in. And so what that means is what we define as the north on Earth is really the south pole of a magnet. That doesn't stop people. We understand that's an issue. We just still call it north. And so we'll say Earth has the magnetic north pole. Magnetic North Pole is just the point that the compass points to. And yes, the magnetic North Pole is the South Pole of a compass. It's weird, but the magnetic north is just still what we call that. Fun fact, that is not the same as the geographic north. That if you view the Earth as a big spinning sphere, which it basically is, the geographic North Pole is the top spot of the planet and is the highest point. But due to the tilt, geographic north and magnetic north is not the same. If you're standing at the North Pole, the very, very top of the Earth, and had a compass, it would be pointing 1,000 kilometers off to the side. That the geographic North Pole and the magnetic North Pole are near each other, but not quite at the same spot. The same is true for the South Pole. But once again, the North Pole is really the South Pole of a magnet, but no one uses that terminology. Okay. Also, the last weird ass thing I'm going to do is a current causes a magnetic field. I said that with the electromagnets. That the electromagnets is just a current carrying wire creating a magnetic field. But an interesting thing is that also a magnet can change electric fields. What I have here is what is called a cathode ray. What a cathode ray is a series of electron beam shot through a gas made to glow. So that green line is just a series of electrons. When you have a current carrying wire or an electron beam, which is the same thing. An electron beam is a current, just not in a wire. But either way, if you have moving electrons and you introduce a magnetic field, it can cause the beam to move. Now, when I add this magnet and add one to the behind it, either north or the south pole, you can see that I cause this beam to either go up or down. I bend the beam. Here, I'll keep it full screen for a second. That the one pole makes it bend up, the other pole makes it bend down. This is because a magnetic field will affect a current. What it is a magnetic field will bend any moving charged particle as long as the charged particle is moving, so a current or an electron beam like here, and if the magnetic field is perpendicular to the movement. If the B field is this way and the electrons are moving this way, nothing will happen. It'll only be if the electrons are moving this way and you make it perpendicular. That's why when my electron's moving to the right, I add a magnetic field pointing at us, it moves up. If I add a magnetic field pointing away from us, it moves down. It all works perpendicular to each other using something called a cross product. Once again, that is calculus, not getting into it. This is how an old cathode ray TV works. Is it shoots electrons at a screen and uses electromagnets to bend them to face various things. Modern TVs do not use this. Questions? Okay. That's the end of chapter 8. That's the end of everything on chapter 2. So I'm going to review chapter 2 on Monday, but I figured today I might as well give a little bit of a breakdown. It's going to have 4 pages. The full page will be chapter 5. Make sure you know how temperature affects matter. Know how to do temperature unit conversions. I'm not going to give the conversions. Know how to deal with heat. Q equals mc delta T and Q equals ml. Have that multicolored table I would recommend. And know the ideal gas law and the mechanisms for heat transfer. The mechanism of heat transfer being conduction, convection, and radiation, and the ideal gas law being PV equals NKT. For chapter 6, know your types of waves: standing, traveling, longitudinal, transverse. Know the relationship between frequency, period, velocity, and amplitude. Know how to deal with standing waves, how to deal with light waves, how to deal with sound waves, and decibels, and the Doppler effect. Chapter 7, know your law of reflection. Know how to make a diagram for a curved mirror. That will be on there. Know how to deal with refraction and Snell's law, and also the index of refraction, and how to do lens diagrams. That will be on there. And look at polarization, diffraction, and interference. And for chapter 8, know how to do a charge and Coulomb's law, electric fields, Ohm's law, the relationship between current, voltage, and resistance, and also how to find power, and the equations for resistors in parallel and series, and just some base information on magnets. There's no equations for those that I taught you, at least. Any questions? The most quiet of classes. Okay, we'll stop there. Let me know if you have any questions. Have a good day.